Here we know we will use the normal distribution because it says something is normally distributed. There's a given mean and a standard deviation for the specific distribution. So part A, we select one woman, or the sample size is 1. We want the probability that the weight let's call x, is above or greater than 172 pounds. It's a pretty direct application of the normal distribution. We talked about 2 examples in class, or 2 methods. First thing we had to do was find the z-score. Z is x minus the mean divided by the standard deviation. For this case, that's 172 minus 143 divided by 29 for the numbers that have been given. So let's put it right here. 172 minus 143 divided by 29 is exactly 1 standard deviation above the mean. Number 2 was to find the probability that any z-score would be greater than this one, this new z value. So we took the x value, turned it into a z. We'll look at the table for this value. We can either do 1 minus the probability or the table value that we get. So let's go see this table value at 1. Cook up the table here. 1. Positive 1. 1.0. 0.8413 is the area to the left, but we wanted the area to the right. So to get the area to the right, 1 minus 0.8413, if I recall correctly. 8413, good. Would be the area to the right of the leftmost area. Let's see what that is. 1 minus 0.8413 is 0.1587. Area to the right because it's a greater than problem. Right, here's our distribution. Mean is 143. 172 is here, and we wanted the area to the right. So alternatively, we talked about how to do it with this calculator. The calculator function we would want would be the normal, because the distribution is normal. CDF for cumulative distribution function. Cumulative, all the values from 172 until huge, until 1,000 or 1,000,000 or something sufficiently large, with the given mean 143 and given standard deviation 29. So that does both of those 2 steps previously in one fell swoop. Second, variables for the normal CDF. The lower bound now is 172. Upper bound of huge. Mean of 143. Standard deviation 29. If you have the calculator without the updated operating system, make sure to enter those guys separately, same entries, just separated by commas instead in the linear form there. 0.15865, so 1587. Hooray, look at that. They match. So life gets interesting, however, in part B. Now we have 5 women randomly selected, and we are talking about the probability of a mean weight more than 172. So before it was the probability of an individual weight. Now it's the probability of a mean weight, x bar, greater than 172. So that changes some things. According to the central limit theorem, this is a new distribution for x bar. It has the mean of x bar, still the mean, 143, but the standard deviation of the sample mean x bar is the old standard deviation, 29, divided by the square root of the sample size. That will change our calculations here or here, anywhere that the standard deviation was used previously. Otherwise, the process is exactly the same. So let's see if we can do that. Part B, our sample size is 5. We want the probability that x bar is greater than 172. We have a mean of 143 and a standard deviation of 29 over the square root of 5. So in the two-step plan, number 1, find z. This is x minus the mean divided by the new standard deviation. We have the standard deviation of x bar, or if you like to just do it all at one time, x minus the mean divided by regular sigma divided by the square root of the sample size. X still 172, the value we care about, mean still 143, divided by now though the adjusted standard deviation, 29 divided by the square root of 5. Definitely we'll need a calculator for that one. And it's sufficient to put it all in there with with parentheses, 172 minus 143 divided by more parentheses, 29 divided by the square root of 5. That'd be the fastest, I suppose. 2.236. Alternatively, you could do them in smaller steps, like the top and then the bottom, and then make the division. Step 2 is look this up in the table. We want the probability of z greater than this 2.236, but in the table we only have 2 decimal places, so we have to go to just those 2 decimal places to look it up in the table. And then again, because it's to the right, it would be 1 minus the value we get from the table at positive 2.24. So let's check that out. 2.24. 2.2 is here. 2.2 and 4. So 0.9875. 1 minus 0.9875 is the area to the right. Same picture as we drew before. The new numbers. 1 minus 0.9874 is 0.0126. So the adjustment, that small adjustment in the standard deviation, changed the old probability of an individual, almost 16%, to just barely 1% down here, because we are talking about sample means. Now, of course, there's the calculator method, so we could have put all this into the calculator. Still a normal CDF problem. The mean is, or the min is still 172. That's where we start counting the weight up to something huge, 10,000, a million, whatever feels good to you. The mean is 143, and the standard deviation now has been adjusted, 29 divided by the square root of 5. So we put that all in here. Second, variables or the distribution menu, normal CDF to find probability. All our other numbers are good, but we want to adjust the standard deviation by dividing by the square root of 5. Reduction in variation from looking at the sample means. Even if you're entering in line, see how you can do that? 29 divided by rad 5. Let the calculator do all the heavy lifting for you right there. And we find this probability to be gone. 0.0127. So it is a little different in that 4th decimal place, but just barely, and that's because of the cost of rounding here and not being able to be more accurate because of the table. The problem will be very similar for part C, except instead of 5, now there are 99 women selected. That will make this probability go down even more. From 1, we saw 0.15. For 5, we saw 0.01. For 99, we're going to see something very, very small, like close to 0.